Okay. Good afternoon, everyone. Let's start. So first, our homework 5 has been released. So you could start right now, and we hope that we're gonna have one more homework assignment. Then that's it, and then we'll probably will spend one lecture talking about how to review the final exam and walk through the major points we have discussed. And by the way, anyone who wants to retake quiz 8, which may involve some content we have discussed this week, please just shoot us an email, and we'll just set up the quiz so we can have one more trial. Feel free to shoot us an email, and I hope that we're gonna have anyone who is willing to retake the exam like by this Friday. Any question? Okay, great. So let us continue with the definition we discussed at the end of last lecture. So in the last lecture, we first revisited the properties called linearity of for expectation. So what does it mean? It means that if you have a function of say 2 random variables, g, x, y, this function is a linear function, meaning you're gonna linearly combine these 2 random variables with coefficients r and s, and r and s here are just constant coefficients. There are no random variables. So when we calculate the expectation of this linear combination, Rx plus Sy, we can decompose it as a linear combination of the expectation of X and expectation of Y. Sorry. In terms of these coefficients R and S. So you see that it's like I'm gonna apply the expectation directly over each random variable, then do the linear combination. So this is called a linearity. Right? So with the concept of the joint PDF and marginal PDF, we're able to show this property. Right? So we're not gonna repeat this, but we just want to highlight the idea of the proof. The idea is that, okay, we start with the definition, right? If we want to calculate a function of the random variables, what shall we do? Any thought? If you want to calculate the expectation for a function of random variable, not a random variable itself, it's a function of random variable, what should we do? Yes, exactly, right? So you're gonna integrate the function of the random variable multiplied by the joint density. Let me write it in a more good looking way. Multiplying with the joint density function of x, y, and over x and over y. Right? That's how we calculate the expectation for a function random variable. So if we leverage the form of G, which is a linear combination of Rx plus Ry, right? and then multiply with this drawing density function, we can just, put the integration over every term, right? And then you integrate every term, say Rx times Fxy, and for double integration of x and y, you're going to marginalize out one variable first, then do the integration with another variable. You will find that eventually we arrive at computing the expectation of x first and the expectation y first, then multiply them by the coefficient r and s respectively and add them together. So we highly recommend everyone replicate the proof by yourself. So to strengthen your understanding about those definitions, like marginal density function, drawing density function. How do we get marginal density function from drawing density function? We're not going to repeat here. Okay, any question? Okay, and then we introduced the definition of covariance, right? So covariance is defined as a function of two random variables, x and y. These two random variables, the covariance itself actually is an expectation of these two random variables. That means you're going to have some function g of x and y. Then you take the expectation of g, you get covariance. And here, this g takes this form. So this is not a linear form. It's not a linear combination of x and y. Instead, it is nonlinear form. It is the multiplication of the difference between x and x expectation and the difference between y and y expectation. So this guy forms our definition of g. Then we take expectation of this function of x and y. Okay. Any question regarding the definition? Okay. So if we set one of the two variables to be identical, say if we put y as x, that means we're computing the covariance between x and x itself, then the covariance is reduced to the variance of x. So what's the definition of variance? For anyone? And you need to add a square. Yeah. Okay, great. Yeah. So the variance of a random variable is the expectation of the square of the difference between x and its expectation. Right? So if you double check this, right? If you substitute x for y, right? You see that the formula is immediately reduced to the variance. Right? So what's the meaning of the covariance, right? What kind of like intuition underlying the definition? So covariance represents in certain degree how much the variable x and the variable y vary together. So what does it mean? Like, imagine this axis represents the value range for x, and this axis represents the value range for y, right? So you got expectation of x here, you got the expectation of y here. Okay. So x is random variable, y is random variable. It's kind of mapping some random experiments outcomes to numbers, right? So imagine if you do those experiments many times, you are gonna observe the values of x, right? So if you got the positive covariance of x and y, what does it mean? It means that, okay, when you do some like numerous experiments for x and y, right? Most of the time, like when you observe x is on the right hand side of its expectation, that means y are on the right hand side as well. Namely, x and y are varying toward the same direction. Or when x showing up to be on the left of its expectation, then y will be observed most time on the left of its expectation as well. That reflects that, okay, x and y are changing or varying in the same direction. So you got the positive covariance value. On the other hand, if you see the covariance value, covariance between x and y is negative, it just means like they're varying along the opposite direction. Right? So when you see x appearing here, right, then y is more likely to appear here. Or when you see x is taking here, then y is more likely taking here. That's why you see after you calculate expectation, after you calculate the covariance, which is an expectation, right, their signs will flip, right? These two difference, right? Their signs will be different. That's why you see on average the covariance is negative. Question? Okay, great. And what does the skew of covariance mean? See, for some x and y, I got for some pair of x, y, you got covariance to be 0.8, right? For some pair of covariance, say x, z, you got covariance 0.1. What does this difference in skew imply? It implies how consistent these two random variables vary. So if you observe x is very far away from its expectation, and meanwhile, y will also be very far away from its expectation. Or if you observe that x is close to its expectation, y is also close to expectation, then on average, the expectation of their product will be large. I mean, in terms of the skew, not the sign, right? So that basically means like, okay, they are strongly correlated. They have a larger covariance value. In contrast, right, if you say, okay, x is very largely, but y is just still close to y, right? Or x is close to its expectation, but y is far away. Or when you say x, the difference between x and ex, you say, okay, it seems like irrelevant to how far away y will be from its expectation. That means, okay, the degree to which x deviates from its expectation is somewhat less related to the degree to which y is from its expectation. In such case, the covariance skew is small. Question? So that means like they have a small covariance. Yeah, small covariance is not variance. Covariance is always like it's talking about two random variables, right? Variance is just for a single random variable. For covariance, larger covariance skews always indicate that, okay, they're varying. It's not about like the direction they are varying. It's about the degree they are varying. If the degree of these two random variables are varying kind of like match well, that means, okay, if X deviates much from the expectation, then Y also deviates much from expectation. Or if X deviates not much as expectation, then Y also deviates not much as from its expectation, then the covariance will be large. But if the deviation of X kind of like irrelevant or less related to the deviation of Y, then the covariance is relatively small. It just represents, okay, if X, Y, the covariance not only measures like whether this X, Y varies along the same direction or along different directions, but also varying whether the degree of the variation are consistent or not. Okay, any question? That's why covariance is always kind of like intuitive metric to look into the relationship between two random variables. And we'll talk about later about the relationship between covariance and independence between the random variables. Okay, so here we want to give you some kind of extreme case, help us to understand definition, right? So as we mentioned, right, the covariance measures, sorry, how these two variables are varying along toward the same direction or different directions, right? So if we take y equals to take y equals to x, that means x and y are the same, right? In this case, you know, x and y must vary in the same direction, right? Because y is the same as x. Does it make sense? Right? If I set y, if we set y as x, right? So we know, okay, x varies and y, which is also x, also vary, and also the variation is exactly the same compared to its expectation, right? So that means the covariance of x, y must be positive, right? This is your x, this is your y, right? So you know that y actually is equal to x. Then you know when you see x here, then you see y here, right? When you see x here, you see y here because they are the same random variable. So that means this x and y, the pair x, y must vary along exactly the same direction. Right? They're either bigger than the expectation or smaller than the expectation. And this can be verified by looking into the case, right? What does the covariance mean when you take y equals to x? As we mentioned, when we take y equals to x, the covariance is the variance of x itself. We know the variance is always non-negative, right? So which kind of confirm the positivity of the covariance in this case. Question? Everyone feels comfortable? Okay. So let's see another case, right? So suppose now I set y to negative x. So now I would like to know whether the variation of x and y are going in the same direction. No. They should go opposite direction, right? Right. So imagine you got x, right? So when you see x is here, then your y, which is negative x, would be here, right? 2. And we will see x here, your negative x will be here, right? So that means like x and y in this case should go in opposite direction. As the result, the covariance of x, y must be a negative, right? Let's verify this, right? So according to the definition, the covariance of x and y is the expectation of x minus ex times y minus ey, right? So now you set y to minus x. So you just substitute into this definition. You got expectation x minus ex still there, but you now times y is minus x, right? So here is minus x subtracted by expectation of minus x, right? So what does this mean? What is the negative of the expectation of negative x? Thoughts? So what is the expectation of negative x? Yes, exactly. Right. Following the definition, you see that, right? So if you do the integration, you just move the sign outside. So you can immediately obtain that this guy essentially is just the expectation of negative of expectation, right? We can just switch the negative sign and the expectation. And then you got a minus sign in front of the expectation. So this 2 minus sign become positive. So then our result here will become x minus ex times minus x plus, remember here, right? Plus ex. Right? If we put minus sign here in front of the e, right? This will become x minus ex times x minus ex, right? And this actually is just the square of x minus ex and take expectation. So what's this guy? Yeah, that's just negative variance, right? So you know that the variance is positive, negative variance is negative, right? So that confirms that the covariance in this case is negative. Any question? Okay, great. So this is our original definition of covariance between x and y. But we have an alternative expectation. We have an alternative definition of covariance as well, which probably is more often used for the calculation, proof, and so on. So what is the alternative definition? You can also calculate the covariance between x and y as the expectation of the product of x, y subtracted by the product of the expectation of x and the expectation of y. So see this, right? We just calculate the expectation of the product and the product of the expectation and look at their difference. Their difference is the covariance between x and y. Is everyone clear about this definition? Any question? Everyone's comfortable? Okay, great. So you see this form is looks like much more concise, right? Concise and easy to memorize. That's why in practice, like in calculation or in proof or mathematical derivation, people often use this definition. People often use this form to analyze the covariance. But why this form is equivalent to the original form? So the original form is take the product between the difference between x and minus x and ex and difference between y and minus y and ey, right? And take their product and then take expectation, right? So why this can be simplified to just taking the difference between two expectations, difference between the expectation of product and the product of expectation. So we're gonna show this, right? We're gonna use the linearity of expectation to show this. This is a very famous conclusion, and the tricks we use to show this conclusion is broadly used in the whole like statistical domain. Okay, so let's try to show this, right? So we're gonna start with the original definition, and by arranging the terms, merge the terms, and we see if we can simplify to the second definition. So the covariance xy originally is defined as expectation of this product, right? So now we just expand this product. So we're gonna expand this product and write them into using distributive law, and write them as a combination of 4 terms. I believe everyone has done this before, right? So let's do this. So we got xy and x times e of x, ex times y, plus ex times ey. Is it clear for everyone? Okay. Any question for this expansion? Okay. So now inside the expectation, we see what? A linear combination of these 4 terms, right? Does it make sense? Right? It's just xy subtracted by x times ex, subtracted by ex times y, plus ex times ey, right? They're just 4 terms. We add them or subtracted by them. You can view this just a linear combination, right? The only difference is that the coefficient is 1. Then we can apply the linearity of the expectation. The linearity of expectation says if you're taking an expectation over a linear combination of the terms, you can first do the expectation for each individual term, then linearly combine them. Right? Then let's try to do this, right? So that means we're gonna calculate expectation of xy, the first term first, right? Calculate expectation of x times expectation of x first. Calculate expectation of ex times y first, and calculate expectation of EX times EY. Then we should put the linear combination outside, right? So that means you're gonna fill in between those expectations with the original plus or minus operations, right? So it's minus, minus, plus. Any question? Dot? Everyone feels comfortable? Okay. Oh, oh yeah. You're right. You're right. Thanks. Yeah. So this one is, yeah. Thanks for pointing out this typo. So this is EY, right? So we do this cross term, right? XY, XY, X times EY. So I'm gonna multiply with EY, and EX times Y, and EX times EY. So I'm gonna fix the other terms. Yeah. Okay. Great catch. Any question? Any other question? Okay. So now let us look into those terms one by one, right? So first one, there's nothing you can do with that. You have to calculate the expectation of the product between X and Y, right? So how about the second term? What is the expectation of X multiplied with EY? So first, what does EY mean? Is EY a random variable? No, right? Then what is EY? EY is a constant, right? Yeah, remember Y, you calculate expectation of Y, right? This expectation is not a random variable, just some number, like say 0.5 or 3.7, right? It's just a constant. It's a fixed constant. Then it means what? It means we can actually move this constant outside of expectation, right? Okay. If you do the expectation of any constant multiply with this random variable, well, I'm showing that you can just move this constant R outside of expectation, right? Question? Okay, so I believe everyone feels comfortable at this step, right? So we observe that, okay, expectation of Y essentially is not a random variable. It's just a fixed constant. So to simplify, we can move E of Y, this constant, out of the expectation. And what we can observe is that, okay, we have EY times EX. Right? Okay, let's look at the second term, a third term, this guy, right? What can we observe? Yes, exactly, right? We have some kind of symmetric observation. EX is a constant as well, right? It's not random variable. So that means we can take it out, right? So that means for the third term, we can put EX outside, then times expectation of Y. So now we have some new observation. You see, Now the second, third terms are identical, right? They're both expectation of X times expectation Y. Does it make sense? Okay, so now let us look at the last term. Right? So last term is the expectation of the product of the expectation of X and expectation Y. How can we simplify this term? Yes, exactly, right? This is a very, very important observation. Look at EX is a constant, EY is a constant, right? Constant multiplying with constant is another constant, right? You take expectation of the constant is the constant self. You can just simply remove the expectation. Right? So like EX is 0.5 and EY is 1.0, right? You multiply them together, which is 1.5. I forgot. Anyway, it's still constant, right? Your take expectation is itself. So we can simply remove the outside expectation, right? So we got EX directly multiplied with E of Y. So now what can we observe? We see another product of the expectation. And then when we merge the three terms, what do we get? When we merge the three, the second, third, and the last term, what do we get? Yeah, you got this guy and this guy cancel out, right? So eventually, you only have two terms left. The first is the expectation of the product. The second term is the product of expectation. Question? This is how we arrive at the second definition of the covariance between X and Y. Yeah, we recommend everyone try to apply this simple two steps to show this. And this is like very widely used trick. So you, especially regarding the statistics, right? When you have some like function, polynomial function of the random variables, you just expand the polynomials and then apply the expectations over every polynomial term, and then using and take out the expectation outside of the expectation, and then do some cancel out, right? And usually you're gonna have like a very large simplification of the original expectation of the function. This is a very widely used trick. For example, there's a famous observation in machine learning models, which is called bias and variance trade-off. It's basically say, okay, if you use a very complicated machine learning model like neural network, you're gonna have a very small bias, but you have very large variance because the model is very sensitive to the data you're given. Right? On the other hand, if you have a simple model like just linear regression, and you see a large bias but smaller variance because if you throw data and just perturb the data a little bit, it won't change the learned linear regression model because it's just a line, right? Just a line to try to be close to all the data points. Right? 1 and 2 change, the change of 1 and 2 points won't change much about the location, the slope of the line. And that conclusion is derived by using the same kind of trick here. Questions? Okay, let's rest for a few minutes and then continue. What do you mean by formulas? No, we won't give you that. Yeah. Yeah. Okay. Yeah, let's continue. So now let us take a look at another interesting result. So let us consider if you add the two random variables, x and y, and then what is the variance of x plus y? A question would be, I mean, intuitively, you might think of, okay, this might be just the simple addition of the variance of x and the variance of y. Right? Why? Because we have the linearity of the expectation, right? So expectation of x plus y, we can use expectation of x, then expectation of y, then add them together, right? Does the variance takes the same linearity property, like variance of x plus y equals to variance of x plus variance of y? Any guess? No? Why? Yes, exactly. You hit the point, right? So when we take expectation, only when the function of the when we take expectation for a function, right? Only when the function is linear function, we can do some linear decomposition, right? But the variance is an expectation of a nonlinear function. It's a square function, right? If everyone could remember the definition of the variance, right? So we're taking an expectation to calculate variance, right? We're taking an expectation of a square function, which cannot provide you the linearity. Then what's the relationship, right? What's the relationship between x plus y, the variance of x plus y, and the variance of x, variance y? Let's try to dig this out. We start from the definition, right? So we know the variance of any random variable, here x plus y is random variable, right? Is the expectation of this random, the square of this random variable subtracted by the expectation of this random variable, right? So here the random variable is just x plus y. Okay. Then let's do some kind of like simplification. Right? So inside the parentheses, right? So we got x plus y subtracted by, so here we can use the linearity of expectation. Expectation of x plus y equals to expectation of x plus expectation of y, right? Question? Okay. Then let's do some kind of a little bit association rule, right? So we got four terms inside this square, right? So let's just combine x with expectation of x. And then we combine y with expectation of y. And then add them together and take a square. Does it make sense? Right? You see, for these four terms, I will just arrange them, rearrange them, right? We put x and minus ex together, y and minus ey together, and then you're gonna still take the square of the summation. Does it make sense? Okay, and then we can treat x minus ex as a whole, then y minus ey as a whole, right? This is just a plus b square, right? So just expand it. What can we observe, right? So x minus ex, you're gonna take square, right? And the y minus ey, you're gonna take a square, right? And then what else do we have? What else do we have? Like consider you're expanding a plus b square. You got a square, you got a b square. What else do you have? Yeah, you got a 2ab, right? This cross term, right? So here, our a is ix minus ex, and b is y minus ey, right? So when you do the expansion of this square, you're gonna have a 2x minus ex y minus ey. Question? Then let's apply the linearity, right? So you can view like this term plus this term plus this term, right? And add them together, take expectation is same as you first take expectation and then add them together, right? That's the linearity of expectation. So which gives us expectation of x minus ex squared plus expectation y minus ey squared plus 2 times expectation x minus ex y minus ey. Do we agree? It's just the application of the linearity of the expectation. So now let's see what are those terms represent. So what does the first term represent? Thoughts? Yeah. The first one is variance of x. How about second term? Yeah, variance of y. How about third term? Can anyone speak louder? Yes. And then the third term is simply 2 times the covariance between x, y. Now we get the results, right? We get the result. That is, when you calculate the variance of x plus y, you're gonna need not only the variance of x, the variance of y, but also you will have 2 times the covariance of x and y. So that's the conclusion when you do the variance over the addition of 2 random variables. And it's very important formula. Something is like if you when you calculate when you calculate the covariance of the variance of the sum, you need to not only consider the individual variance, but also you need to consider the covariance. Question? Great. So when do we have the variance of x plus y equals to variance x plus variance y? We see that only when their covariance is 0. Could anyone think of like when the covariance between x and y will be 0? Yes, exactly, right? Intuitively, if X and Y are independent to each other, then their covariance must be 0, right? And in this case, the variance of X plus Y will simply be the summation of variance of X and variance of Y. But why the two random variables are independent? The covariance must be 0. This actually can be proved directly from the definition. So we just do a quick proof. Hopefully, it will practice our understanding about those concepts. Right? So we know the covariance. We're going to use the second definition of the covariance for simplicity. So expectation of xy subtracted by the product of the expectation, right? So for this guy, we know it is just the xy times fxy, right? Sorry, let me write it a more beautiful way. So you're going to multiply xy with the joint density function of x and y and dx dy, right? This is definition. Xy is a function of xy, right? X and y, right? If you want to calculate its expectation, you're going to multiply it with the joint density function, then do the double integration. And then because xy, when xy are independent, right? That means this joint density can be decomposed as the marginal density of x and marginal density of y. Right? That's the definition of independence. If x, y are independent to each other, then their joint density function is the product of their individual marginal density functions. So if you're doing this, if we have this, right, that means our integration can be immediately decomposed, right? So we can do x times the marginal density of x and along with x first, right? And y times the marginal density of y along y second, right? The integration of the marginal density of y multiplying y has nothing to do with x, right? So we can do them first. And for the remaining, you got integration for x times the marginal density for x, right? It has nothing to do with y, right? That's why you can do the association law and then do the integration first and multiply together. So what does this term mean? Expectation of x, right? And the second term, expectation y, right? You see that when x and y are independent, then the expectation of x and y is the same of expectation of x times expectation of y. As the result, you further to calculate the covariance, you further subtract this guy with the expectation of x times expectation of y, which will be 0. Question? Okay. So for convenience, we usually use a sigma square as the notation for the variance of a single variable. See, this subscript x denotes that, represents that, okay, this is a variance for the random variable x. So if you want to look at, if you want to denote the covariance between two random variables, right, then we use the subscript x comma y to represent it. So sigma x comma y denotes the covariance between x, y. Okay, so now we have a showing an important fact. If two random variables, x and y, are independent, then the covariance between x, y is 0, right? This can be directly proved through the definition of the covariance. I'm showing that. Right? But now, one tricky thing or one tricky fact everyone should be aware. If you got zero covariance, it doesn't mean X, Y are independent. You see that X, Y are independent to each other. You can directly arrive at the conclusion the covariance of X, Y is simply zero. However, when you say the covariance between X, Y is zero, it doesn't mean X, Y are independent. So that means X, Y are independent are just a sufficient condition for zero covariance. Zero covariance doesn't lead to independence. Actually, covariance represents a special type of independence, right? And in the future, probably you're going to study more in depth about statistics and probability theory. The covariance actually represents the linear dependency between the random variables. However, there could be some nonlinear dependency between the random variables. That's why even you got zero covariance, you cannot exclude, you just exclude linear dependency. Right? You cannot exclude the nonlinear dependency. That's why you could not say the X, Y are independent to each other. Independence means that, okay, X, Y are not dependent to each other in any way. Okay. Okay. In practice, people will not only look at one pair of the random variables, right? So say suppose you calculate the covariance for X and Y, which is 0.8, right? Then you calculate the covariance between Z and W, which is 8.8. Can we conclude that, okay, Z and W, they're more correlated than X and Y? Can we conclude this? See, let me repeat it again, right? The covariance, the definition is expectation of X minus expectation times 1 minus expectation of Y, right? So now suppose you have one pair of the random variables, X, Y, you calculate the covariance is 0.8, and you have another pair of the covariance like Z and W, you calculate their covariance is 8.8. Can we accordingly conclude that Z and W are more correlated than X and Y? Can we? Any guess? Actually, we cannot. Why? Right. So imagine like we're not consider another pair, right? Let's just multiply X and multiply Y, right? I'm gonna multiply X by 10. I'm gonna multiply Y by 10. So what is the covariance between 10X and 10Y? What's that? We know that the covariance between X, Y is 0.8, right? Now I just multiply X and Y by 10, by a factor of 10, right? So then what is covariance between 10X and 10Y? You feel it's 8? Why is 8? Yeah. Yeah. So, I mean, your answer is at the right direction, but the number is a little bit different than from the correct one. So remember, you're not only multiplying x by 10, right? You're also multiplying y by 10, right? Look into this formula. Right? So we can just do some substitution, right? So now you're gonna replace x by 10x, right? So 10x, subtract the e of 10x, and multiply 10y, subtract the e of 10y, right? You see, for each term, for each parenthesis, you have a factor of 10, right? So what's the result? Yes, it should be 80, right? Because you multiply this two factors, right? Each factor is amplified by 10, right? So you're gonna have a 100 times of the original result, right? Which is 80, right? But obviously you don't see any sense saying like 10x and 10y is more correlated than x and y, right? They should be have the exact same correlation level, right? They shouldn't be affected by the skew. That's the issue about the covariance definition. Okay? The covariance skews with the variables, right? If you multiply the variables by some skew, you're going to skew the covariance as well. For example, if you multiply xy by 0.y, right? If you look at covariance of 0.1x and 0.1y, then the covariance will be 0.008, right? Of course, it makes nonsense saying that after you skew them with 0.1, then their correlation becomes much, much smaller. They should stay the same. So how to address this issue? We want to introduce a metric that is invariant to the scaling. That brings the correlation. It's actually, the full name is called Pearson correlation. The idea is pretty simple. I'm just normalize the covariance by the square root of the product of their variance. So you divide the covariance of xy by the square root of variance of x multiplying the variance of y. So the square root of variance of x is actually called a standard deviation, right? Standard deviation. So actually you're normalize the covariance by the product of the standard deviation of these two random variables so that you can offset the scaling effect. And it's fairly straightforward to show that if you skew x with r and s, y with s, where r and s are non-negative, right? It's non-zero, right? And it is exactly the same as the correlation of x and y. So it is invariant to scaling of the random variables. That's why in practice, when people compare with the relationship, the strength of the relationship between pairs of random variables, they often use the correlation coefficient rather than the covariance itself. Question? Okay. correlation coefficient is a skew-free measure of dependencies. So the correlation is not only used to in practice to compare with compare different pairs of random variables. It is also used to construct the so-called bivariate Gaussian distribution. So we have introduced the Gaussian distribution for a single random variable, right? We say a random variable x, its PDF function takes the particular form. If you could remember, it is something like this: 2 pi sigma x exponential 1/2 sigma x squared x minus mu x squared, right? So if your random variable x, its PDF function has this form, then we say x follows a Gaussian distribution with mean parameter mu of x and with standard deviation parameter sigma x. But the Gaussian distribution can be expanded to multiple variables, not just for single variable. In this case, if you got multiple variables, right? Say, if you got x and y, right? If we say this pair of random variables follows a Gaussian distribution, then this is a bivariate Gaussian distribution. When x, y are independent, the joint probability density function of x, y is simply the product of the marginal density function for x and the marginal density function for y, right? If you do this together, you see this is their, if you multiply them together, you see this is their joint density function. However, what if x and y are dependent, right? They're not independent. Then how should we obtain, or what does their joint density function look like? As we previously mentioned, right? If x, y are independent, then their covariance must be 0. And similarly, and accordingly, the correlation coefficient must be 0, right? But if the correlation coefficient or the covariance is 0, it doesn't mean x, y are independent. But in Gaussian distribution or Gaussian random variables, the correlation being 0 is equivalent to independence. That's how this type of that's the key property of this type of random variables. And the joint probability density function in this case will be decided by the correlation coefficient as well. So this is the probability density function for x and y jointly when they're dependent. Okay. So we see that in the constant factor, you have this square root of 1 minus rho square. Rho is the correlation coefficient we just introduced. And in exponent, in addition to this term, we got a third term. We're going to subtract it by 2 rho and x minus mu x, y minus mu y, and divided by the product of the standard deviation for x and y. So this forms this gives the general form of the joint density function for two Gaussian random variables. So you see that when x, y are independent, that means the correlation coefficient is 0. Then it reduces to the special form where x, y are independent. Okay, let's stop here today. Next week, we'll start reviewing this bivariate Gaussian distribution again because it's very, very useful and important.